My biggest concern when it comes to these systems is that, of course, it's an inherently neutral technology, but in the wrong hands, it could even today be used for destructive and evil purposes. And I don't know how much the regulations that we see right now are addressing that. So a lot of the regulations have to do with how we end up developing these models.
Good morning, good afternoon, or good evening, depending on where you're listening. Welcome back to AI and the Future of Work. Thanks again for making this one of the most downloaded podcasts about the future of work. As always, I'm your host, Dan Turchin, CEO of PeopleRain, the AI platform for IT and HR employee service. I'm also an investor in and advisor to more than 30 AI-first companies. And as you know, a firm believer in the power of technology to make humans better. We learn from AI thought leaders weekly on this show. And of course, the added bonus, you get one AI fun fact. Today's fun fact, the AI executive order heard around the world was issued October 30th by the Biden administration. It's the most comprehensive summary of how the current administration is thinking about regulating AI. Key themes include the development of a national registry for foundational large language models, the requirement for vendors of those models to share their safety test results, and directions to certain federal agencies like the Department of Commerce and the Department of Energy about how to oversee AI safety. The EU has a significant lead in AI regulation, with many countries having already issued more detailed frameworks. The US may catch up if Congress acts quickly to turn any or all of the president's recommendations into law. Issuing an executive order is easy. Defining and enforcing what's there will be much tougher. I encourage everyone to listen to the great recent episode of this podcast with Credo AI CEO Navrina Singh about what's happening now to accelerate the enforcement of these and related regulatory frameworks. As always, we'll link to the full article in today's show notes. Now shifting to this week's conversation. Babak Hodjat is the CTO of AI at Cognizant, the $34 billion market cap provider of tech services with more than 350,000 global employees. He's the former co-founder and CEO of Sentient and is responsible for the core technology behind the world's largest distributed artificial intelligence system. Prior to co-founding Sentient, Babak co-founded and was the CTO and a board member of Dejima. He's the primary inventor of Dejima's patented technology applied to intelligent interfaces for mobile and enterprise computing. That is the technology behind Apple's Siri. Babak has 31 granted or pending patents, is a published author, and one of the most respected thought leaders in AI. He holds a PhD in machine intelligence from Kyushu University in Fukuoka, Japan. And without further ado, Babak, it is my pleasure to welcome you to the podcast. Let's kick off by having you share a bit more about your background and how you got into this space.
Pleasure being here. Yes, I don't remember when I was not in this space, actually. I was in college, and there was a particular day when I thought I figured out how the computer works, and that's the day when a friend of mine challenged me into figuring out how the brain works, and that was the journey started in AI, and I've been in AI ever since, both in research as well as starting 3 companies in AI and working in larger companies. And my passion is, when you're in the lab and you're running these algorithms, you do see the power, even all the way back 20, 25 years ago, of these algorithms. And you want others to see and benefit from it too. So there's an applied side to my career as well when it comes to AI.
You and I have both been in and around the space for more than 2 decades. And I'm going to go out on a limb and say, like me, your definition of what AI is has evolved over the years. How has your thinking about the technology changed?
Yes. When you start, you think, okay, there must be an algorithm running in our heads, and let's try to figure that out. At least that was the case for me. And then after a while, you start defining what are the manifestations of intelligence that we encounter. And it becomes bigger than intelligence in the brain from some respects. On the other hand, it can be defined to operate in a smaller scope as well. So you have both of those options. And I think the field has been successful in both counts. In other words, let's try to make it smarter in many of the aspects of intelligence we know of than humans. And we've been successful in doing that if we pick these aspects separately and looking at them in isolation. And then there's the other aspect, which is, okay, let's try to simplify the domain in which intelligence is being applied and see how well it can do in that simplified domain, which is also, I think, something that we've been successful at. It ebbs and flows, this focus on whether or not we're creating a general intelligence versus, no, it's an intelligence applied to a certain specific use case, and then back to, no, it is general intelligence. And I think we're still going through that oscillation in the field right now.
I like that term, manifestations of intelligence, because it implies a more nuanced definition. One of my concerns about the impact that LLMs have had on the public's perception of intelligence is that it distills what intelligence is down into a very narrow set of, I will call them, parlor tricks that LLMs are designed to do very well, when in fact, I believe that intelligence is a much broader topic. And I'd love to get from you your perspective. You use the term manifestations of intelligence. What are maybe some of the manifestations of intelligence that might imply that we're further from what anyone would call artificial general intelligence than what the foundational LLM models might suggest?
A very important one is that intelligence, at least in humans, manifests itself in an embodied manner. And fundamentally, LLMs do not have that. As humans, we are born with, the capability to exhibit intelligence in tackling problems and predicting what's going to happen and making decisions and being creative and so forth. But all of that is actually applied and learned and improved in an embodied manner. It's my intelligence as a person, operating in that, timeline that starts with my birth, continues with my life. Whereas an LLM is basically absorbing a snapshot of the internet, essentially, and learning from this operating system of intelligence we know of, which is language, and trying to, essentially predict what is the next token in a string of tokens. And by virtue of doing that, predict what we would expect an intelligence system to manifest. And so in that respect, it's very different. What does that mean? That means that we can change our minds. We can encounter a new situation, be creative about it, and these systems can't because they're not embodied. We can look at things like consciousness, and that is something that it's difficult to character, let's say, personality. It's something that's very difficult to pin down in an LLM. It could have all the personalities in the world and none of them at the same time. And so there's a fundamental difference between the two. That doesn't mean that LLMs are not fascinatingly powerful. These systems are able to do things we thought would be very difficult, if not impossible to do, when it comes to understanding language, when it comes to utilizing language, reasoning, poetry, translation from one language to another. These are things that these systems are showing. And I think of LLMs as this proof of existence. There's at least one way, which is through language modeling and a specific kind of architecture, that a deep learning system trained on, a snapshot of the internet can have this emergent behavior, much of which we associate with human intelligence, that up until a few years ago, we did not expect, starting from such simple first principles, to be able to attain. So I don't want to belittle what we've stumbled upon with LLMs. These systems are very useful and very powerful, but also very different than the type of intelligence that at least we see in humans.
It's very easy to talk about next word or next token prediction and make it clear to the public why there are obvious limitations of LLMs and why they hallucinate and explain some of their bad behavior. But as a technologist, I got to ask you, have there been times when you look at you call them emergent properties or capabilities of LLMs and just set aside, a willing suspension of disbelief that where you're surprised that they can do things that transformer architecture, maybe we never even thought it was capable of doing?
Absolutely. Absolutely. I think it's, again, for those of us who are in the field and understand how these systems are put together, it's very easy to be dismissive of this accomplishment and say, oh, it's just, coming up with a probability distribution on the next token. And therefore it's stochastic. And therefore, as you go forward and predict more tokens, you're in uncharted territory. It shouldn't work. But the reality is, in many cases, it is working. And I think we need to learn from that. The fact that starting from such a simple first principle, just predict what's the next token in a string of tokens. Just from that, we are getting this kind of capabilities emerging from the behavior of the system should teach us a lot about the nature of intelligence, even in humans. It's one of those aha moments when you think, as humans and higher order animals, that is what we do. We try to predict what's next. That's all our brain is about, is trying to predict what's next and then take the proper action around that. And so maybe that is the first principle that allowed us as humans to be able to be intelligent the way we define it. So I'm not dismissive of that at all. The fact, though, is that I don't think that our brains use back propagation. I don't think that we have a fixed structure like these transformer-based architectures at this scale that is so difficult to readjust and train. If anything, we think human brains are very plastic. Brain plasticity is amazingly flexible in reassigning at very low energy levels different roles and absorbing different beliefs. And clearly, the current trajectory and the way we're doing large language models right now does not lend itself to that. So I think again, taking it as a proof of existence is a good idea and learning from it, but trying to get there using a different path, maybe also having embodiment as a requirement, might actually help us achieve more. So big milestone, but much more still to do.
I believe that imbuing sentience onto large language models is doing a disservice to the public. And I believe that there are a phenomenal number of use cases that are well applied to large language models, but we vastly exceeded where they are and are not useful. And yes, that's me on a soapbox, but I would love to get your perspective. Maybe one thing that you're seeing attributed, or a capability or a use of large language models where you feel like it really exceeds the boundaries of what that technology is optimized to do.
Yeah, unfortunately, we in the AI field, we always have to deal with the problem of expectations. And again, our expectations of these large language models have far exceeded their capabilities. One of the expectations I see a lot is, here's this one model that is intelligent, and so ask it anything. And so we expect it to actually be able to pull from its training set and be able to answer any questions that we ask it. So the first step that people take in utilizing large language models is this: here's the model, let's request it to do stuff for us. And I think that's the wrong way of making use of these systems, because it contradicts the whole point in training the large language models and on a very large corpus. The reason why we train them on language modeling was to get them to abstract from that data set and abstract in a manner that's analogous to how humans abstract the world. Not to be a knowledge retrieval system. We know how to build those. Those are not very hard to build. You can use a search engine and find stuff on the internet. That's not very hard to do. What we've tasked the systems are to abstract. And by virtue of that abstraction, it seems like they've been able to understand language to the point where they can respond correctly to most queries and be able to do some level of reasoning and machine translation and all that kind of good stuff, write code. So if that's the case, let's use it in that context versus, opening ourselves into all sorts of limitations because the system was only trained once and it has a snapshot of the internet and it wasn't really trained to remember everything verbatim and rote learn it. It was actually trained to abstract. And the right way of thinking of these systems is, in fact, to move away from this AGI concept of an LLM to an agent-based concept of the LLM, and which is really interesting because it looks like we've come full circle again, which is, take a large language model and give it a contained problem to solve and engineer it in a string of other large language models and potentially other types of capabilities in order to achieve something. And, it reminds me of the approaches we used in the late 90s, like multi-agent systems, agent-based approaches. And back then, of course, these agents were heavily engineered. Now you have the luxury of being able to just, explain to it in your mother tongue what you expect it to do, but explain that so that its domain of sort of operation is limited. And you're not counting on it to pull from its training, but you're counting on it to be able to operate the API and, interact with other LLM-based agents and ML models and so forth to achieve some sort of a goal. Sometimes it's a little bit difficult to explain to folks that there is still a lot of engineering that has to go into making use of these LLMs. And it's not just, a be-all, end-all piece of software that you just query.
You talked about brain plasticity, and one of the things that I think is not well appreciated is that when we use that analogy of the human brain, we quickly reach the useful limits of the analogy, because even deep neural nets, the learning rate is extremely slow, comically slow, relative to how many times does a toddler need to touch a hot stove before learning not to, right? Versus how many millions of maybe training examples would a deep neural net need to learn on before understanding the same principles. What about kind of the fundamental architecture of LLMs do you think is not well understood when we kind of force fit this analogy of the brain and how the human brain learns?
The fact that this is a caricature of how we think the brain works, it's very far from the reality of actual neurons in the brain and how they're connected and their behavior and how they learn and operate. Obviously, neural networks are inspired by how we think the brain works, but that's the end of it. From there on, we've tried various different ways of getting neural networks to learn. And if this breakthrough in the last 15 years or so has been, debugging backpropagation, which is one way of, through this offline batch training, getting these neurons to settle on a behavior that, as a whole over the network, more often than not gets the training, samples correctly versus incorrectly. So that's basically the way we've done it. Backpropagation is not the only way the brain operates. In fact, a lot of neurologists believe, or neuroscientists believe, that's not even how the brain works. But it works for us. We've not come across an alternative that's more efficient yet to take this kind of substrate, which is a network of neurons, and train them to be able to do, to abstract and learn. And yes, deep learning is a great brand name, but it's neither quite deep nor is it learning the way we think it should be learning, because it's not learning as it goes. That's another one of the misunderstandings out there, is that, if I interact with ChatGPT, is it going to learn? No, ChatGPT is not going to learn from your interactions unless your interactions are stored and labeled and either used for fine-tuning, which isn't technically learning, or appended to the large corpus to retrain a new large language model. These systems are static. They don't learn as they go. And that misunderstanding also gives you a sense of how, expectations are unmet. When we say learning, we really do expect the system to learn as it goes, and it doesn't. It does not. So yeah, that's definitely, I think, a fundamental difference. Again, not belittling the huge breakthrough in large language models and its applicability. I just want to point out that there is this fundamental difference between how LLMs work and how the brain works.
You have a unique background in that you're both a pioneer on the AI side and some of the neural architectures we've been discussing, but you've also engineered these systems at scale. I would love to know, as an engineer, what are the things that you feel like maybe don't get talked about enough that are the really hard problems that took just an academic transformer architecture, from the 2017 Google paper, and all of a sudden gave birth to things that are operating at planetary scale, some of these foundation LLMs, concepts like reinforcement learning with human feedback pioneered at OpenAI. What are maybe some of those things that you see as both an engineer and an AI scientist that aren't well understood?
Yes, just the sheer amount of engineering that goes into making these systems work. You talked about the reinforcement learning, fine-tuning that goes into this. These processes are known to be rather brittle, and they have their shortcomings. You can't just continuously fine-tune a fine-tuned model and not expect it to either completely, forget everything or, converge, or to continuously learn and absorb the biases that you're introducing into these systems. So there's a lot of engineering, some art and voodoo from experience that goes into setting these systems up. There's a lot of work that has gone into scaling them so that we can actually run them on hardware. And I think one of the biggest breakthroughs in deep learning has been the way we've tensorized these models. And so we can actually whoosh in a lot of data and training in parallel. And so make use of, parallel architectures like GPUs. The data itself is amazing, what tricks we have to play to get that scale and level of data through the system. And then there is, of course, what data do you show? How do you show it? How do you distill these models so that they're smaller and yet still functional? Yeah, people, I think, sometimes don't quite realize that this is, and it has never been, like AI has never been a discipline in which you just have an algorithm and it's turnkey and you just turn it on and it works. To get these systems to work, there's a lot of trial and error and a lot of engineering that goes into it, for sure.
So in the opener, I talked a little bit about the executive order about AI safety and new regulatory frameworks. I'd love to get your perspective. What is important when it comes to the ethics of AI and what we'll call casually responsible AI? What does that even mean to Babak?
Yes, my biggest concern when it comes to these systems is that, of course, it's an inherently neutral technology, but in the wrong hands, it could even today be used for destructive and evil purposes. And I don't know how much the regulations that we see right now are addressing that. So a lot of the regulations have to do with how we end up developing these models and less about how we end up using the models. And there are models today that are out there and open source that anyone can download and run and use. And it seems to me like that is the more important part that's maybe somewhat being neglected here as far as how it could be put to ill use. Now, having said that, you talked about responsible AI. I think responsible AI is a very good excuse for humanity to start defining what we mean in an unambiguous manner as to the ethics of technology. And I say technology because we've neglected that with technology, and now with AI being able to be somewhat more autonomous, I think it's high time for us to start thinking about that. And it's only when we start defining unambiguously those ethics that we can start either embedding them in these systems or adding safeguards for them. It seems to me like humanity has always had the fall guy, and it's usually a human being that's there, and we can blame for when things go wrong. And so because we've had the fall guy, we've been able to defer the non-ambiguous definition of what's responsible and what's ethical to after the fact. Like something bad happens and then we go, oh, you were responsible for this thing that I didn't really quite define very well in the first place, but now I know there's an instance right here and I'm going to hold you to account. We can't do that currently, at least, because if we have autonomous AI agents making decisions, we still need, it's like self-driving cars. I need someone to sit and hold this steering wheel, even though they're not doing anything. But the reason why I need that person there is so I can blame them if something goes wrong. That's only going to get us so far. And so I think responsibility is something that we need to define. And it's not enough for us to just look at, oh, here's the data on which this AI is going to operate or train, and let's make sure the data is not biased. The data is always going to be biased. So there's only so much we can do on that data side. I think we need to make sure that on the actual operation and behavior of the AI, that we have safeguards to check and make sure that any decision that's being made is ethically acceptable and responsible. And we can do that several different ways. We could use, for example, large language models to check on large language models to make sure that they're, whatever they're advocating to be done is good. So that's one way of doing this. We can make use of inherently explainable models in that workflow at the point where the decision is being made. So we might have large language models and other black box models making predictions and getting us to the point where we want to optimize and make some decisions. That decision maker, though, better have a explainable set of rules, for example. And that's where we can then check those rules and go, okay, this one seems to be biased, or this one seems to be problematic. So that's also another way of doing this. But ultimately, we're talking about decision making here. All AI and analytics and so forth is, at the end of the day, in the service of some decision that's being made. If a human's making the decision, we have a system to make sure that it's okay. But if a machine is making that decision, that machine will have been programmed to try to optimize certain outcomes. For example, maximize my revenue while minimizing my cost. But it's not the only things we should task our machines to optimize for. We have to add the ethical aspects. I don't want your decision making to hurt people. I don't want your decision making to be biased or give preferential treatment to some folks. Those are other outcomes that maybe right off the top of our heads, that they don't come naturally as outcome objectives for a decision maker, but we need to start defining them and adding them. And that's when our AI is actually solving for the ethics and the responsibility in their behavior and decision making.
So this is a tactical question, but building off of that answer, when we look at open source versus closed source AI, what do you think from the perspective of safety, maybe even scalability, but just responsible AI? Does it make more sense for us to have access to those weights and information about the training data in order to ensure that the AI is used in a way that's safe, or maybe perhaps closed models where the source is trusted? And again, I don't want to bait the witness here, but I'd be curious to get your perspective on the kind of perennial closed versus open source debate within the AI community.
Yeah, let's start by saying that today we really don't have a true open source large language model out there. People do publish weights and you can download them for some models, but you don't really know what kind of training set they were trained on, what kind of methodology was used on the training. You get the end result that is the weights, and you can do stuff with them. That debate is there, and I don't know where I fall on the two. I just intuitively, as an engineer, I think open is probably better than closed. We do have the commercial models, and then we have the open source, but it doesn't quite address the problem of explainability, even with the weights being published. It's still weights of a deep neural network, a very large one at that, and these are inherently black box systems, so it's very difficult for us to know why and how it's behaving. It's like biology. We can poke it various different ways and kind of experiment with it and get a sense of how it's going to operate, but we're never going to be exactly sure because they're inherently black box. But yeah, in the grand scheme of things, I think open is better than closed. But again, it goes back to who is going to get to use it and how, which I think is the biggest risk we're facing with these systems these days.
Hey, Babak, I know the time has flown by, but I got to get you off the hot seat, but not without answering one last question for me. I teased in your bio that you were a developer of some of the foundational technologies that went into Siri. I would love for us to learn something that maybe has never been published about the development of Siri. And if you had an audience of Tim Cook and the team, what would your advice be to actually make Siri seem truly intelligent in a way that maybe it's drifted from the initial vision of what it could be?
Definitely. I do think that the initial Siri or natural language technology behind Siri was revolutionary, but we're talking 25 years ago. And the reason why it was revolutionary was because at the time the state of the art was, language driven. So let's capture the grammar of the language and then the semantics of the language and and then overlay of context and decide what this inquiry means and how we can map it to some functionality. And the big innovation there was, you don't have to do that. As long as you basically model, the functionality that you want to interact with and substitute the various different functions with these idiot savant agents that are looking at the input and essentially making claims on that input. It's like having the ontology of the domain of discourse. And my good friend Adam Chire called it active ontology. So you actually have these nodes within that ontology, all of whom are actually looking at the natural language that's coming in and making claims and deciding, I know how to do this, I know how to do this. And over that network, it would very naturally be able to disambiguate and decide exactly what needs to be done for that input. So that was it seemed like a very elegant approach at the time. It was language independent because we really started from the functionality and the ontology first. And so it allowed us to actually build these systems in various different languages. It was very extensible, like new functionality came in, you could just append it in, and it would then, like the domain of discourse would expand. But it was also heavily engineered. Each node had to be engineered to understand very well how people would potentially refer to it. Yeah, it's high time to change that. And I think we've come full circle here. Sorry, Siri is answering me now. We've come full circle here in that back then the view was an agent-oriented approach. And right now, too, if you look at how large language models are being used, we're giving them a different persona in a sort of a multi-agent system. And I think maybe that's the way to upgrade Siri, is to actually have large language model nodes that are representing various different applications and functionality within Siri, plug in together and work together to understand and collaborate and maybe sometimes interact with the user in fulfilling their requests. But yeah, it's time for us to definitely upgrade Siri and make it better for sure.
That was a very diplomatic answer. And Adam, if you are listening, you have an open invitation to come on the podcast and talk about active ontologies in more detail. That would be an interesting discussion. Well, Babak, we're out of time. One important topic that I would love the audience to hear from you about is, where can they learn more about the good work that you and your team at Cognizant are doing?
Yes, we are at the forefront of making use of generative AI. As a services company, Cognizant advocates pervasive and responsible use of AI across the board. And we've been doing this for many different use cases. If you guys come to cognizant.com and search for generative AI, you can see it on the homepage right there. The platform I'm personally responsible for is Neuro AI. That's also, you can get to it from the cognizant.com website. And yeah, come check it out. It's actually quite powerful and uses a lot of the sort of principles, topics that we discussed today as part of the platform.
We will link to those resources in the show notes.
Awesome.
Babak, this has been such a pleasure. I can't believe it took us more than 250 episodes to get you on the show, but appreciated your insights, and it was great hanging out. And I hope that you too will come back as some of these principles move forward, the technology matures. We'd love to get more of your insights in the future.
My pleasure, Dan. Thank you very much for having me.
That's all the time we have for this week on AI and the future of work. I'm your host, Dan Turchin from People Rain. And of course, we're back next week with another fascinating guest.